Yeah.
I was told that you have an interesting philosophy on global economic theory.
Okay, yeah, I do. I didn't tell you about how many people think the dollars. How many people think the price of oil went up recently?
Went up.
Yeah, I have a theory. Mine is that the dollar went down. Okay, because what else went up? Gold, steel, concrete, everything else in the world went up. So that to me says the dollar went down. Okay. Now the overall theory on the economic, my theory on the world economic theory is, we have a distinct advantage in this country because the world has in the past, although it's starting to change, I think, traded in dollars, and we have the distinct advantage. We're the only people who can print dollars legally. That's not to say we're the only people who print dollars. North Korea does too, but we're the only ones who can do it legally. We actually tend to print more than even the North Koreans do. And so I actually developed this a few years ago when my mother, who grew up during the Depression, said, "What are we going to do about this trade imbalance?" You know, and I said, "We're going to do the same thing we did with the Japanese trade imbalance in the 1980s. When I lived in Tokyo for 1 year working for the Office of Naval Research, U.S. Office of Naval Research, it was 240 yen to the dollar. And back in the 1980s, you were alive, and all, if you remember, if you read the paper when you're in elementary school or high school or whatever, the Japanese were considered to be beating our socks off in manufacturing. Well, I spent a year over there, and I used to look at their manufacturing facilities, and they didn't seem like they were as efficient as ours. And just the whole society didn't seem like it was efficient. I mean, when you have people standing there at the escalators, wiping the handrails for the customers in the department store because the Japanese are so concerned about picking up germs, they have someone with a rag. Well, I don't know how many germs are on that rag. I mean, you know, and they would wipe it just so as you get onto the escalator, they would wipe it just where you put your hand so you wouldn't, you know, it'd be clean. I mean, come on, what kind of efficiency is that to pay people to do something like that? But anyway, the whole society was like that. Plus, the Japanese were giving tremendous price supports to their farmers. The price of rice in Japan was 7 times the world price because of things. And so I looked at this and said, that didn't make any sense. But what we did with what had happened is the Japanese were loaning us money in the 1980s so that we would buy Japanese goods, whether it was ships or steel or electronics or whatever. Basically, the United States was in deficit spending mode. We had the Reagan defense build up, and if you go back and look at things, that was when some of the big deficits were coming along. And who was giving us the money to do that? Well, the Japanese were loaning us money so that we would buy their goods. This is the Henry Ford theory of building automobiles. You pay your workers a decent wage so they can afford to buy a car. Okay, and then everybody gets to the point of being able to buy a car. Well, the Japanese were loaning us money so that we would buy their cars. At the time I was over there, it was about 250 yen to the dollar. Anybody know what it is today? Somebody must have been over there. It's around 105 yen to the dollar. What does that mean? It means we're paying the Japanese back at 40 cents on the dollar of what we borrowed in the 1980s. Because we control, I mean, the world is denominated in dollars and we can print money. Okay, so we're paying the Japanese back in cheap dollars, and now we're paying the Chinese. Mainland China is basically sitting there loaning money to us so we will buy their goods, and they're keeping their yuan, their currency, at a depressed level so that their goods will be cheap for us. And eventually, that can't continue forever. Eventually, even a national government can't afford to keep on loaning out these hundreds of billions of dollars. And so what will happen to the Chinese, and probably we'll get a better deal on things than even that, but I would say in 10 or 15 years, you're going to find the Chinese yuan is, you know, we'll pay them back 20 or 30 cents on the dollar for all the money they've loaned us. Okay? So we get to buy cheap cameras and everything else, you know, computers or whatever today. And the only problem is going to be for our grandchildren, because eventually all this borrowed money is, even if we're paying it back, you know, cheap, And you know, there are other parts of the world we can go. Where are we going next? We're going to India, right? And after we go to India, there's still the former Soviet Union, and then there's Africa. And we've been doing this with South America for the last 50 years. Okay. The only problem there is we end up loaning them money, and then we end up forgiving the loans and stuff. So that's kind of getting old. But in any case, the idea is because we're denominated in dollars, but what you find out is people are now shifting away from wanting to denominate everything in dollars. But the country that controls the world's currency, and we have, is going to be able to take advantage of people who want to loan us money. So we can deficit spend as long as they loan us money, and then as long as we can keep attacking one little area of the world at a time, financially, we'll pay them back in cheap dollars. Okay? That's my theory of the economics. Okay? So the dollar didn't, I mean, the oil, price of oil didn't go up, the dollar went down. Okay? I've actually mentioned this to some economists, and they sort of agree with me. Oh, well, it's not 100%. Oh, okay, well, maybe it's not 100%. Nothing's 100% with an economist, right? You remember what Truman said? Anybody know what Harry Truman said? He needed a one-armed economist. It was on one hand and then on the other hand. Okay? They give me a one-armed economist. And I always say, how do you get five different ideas on any subject? You ask 3 economists. Okay? So, and those are usually mutually exclusive ideas. Okay, other questions? You can go ahead and start, Brian. We haven't already.
Let's start.
Okay. Yeah, ask a question. I got theories on most everything. In fact, this one time, this was back in like mid-1980s, 2 of my graduate students I walked in the lab, and 2 of the graduate students were there, and they asked me a question. And I said, well, gee, I don't know, but, and then I just started thinking my way through it. And they started laughing at each other. And I said, what are you guys laughing at? And they said, you always have an answer for anything. And I said, well, I said I didn't know. And they said, yeah, but then you proceeded to give us an answer. I said, yeah, but, you know, I'm supposed to be teaching you how to think. Okay, so even if I don't know something, doesn't mean I can't figure it out from the basic things I know. Right? So, to a certain extent, I've actually told students in this class before, in years past, I actually consider this class, although you haven't asked as many questions, but if you ask questions, it's actually a chance for me to teach you how to think your way through things. Because I find most people don't know how to really think their way through things. And there are things that you actually know about, okay? Like, later on, I think I mentioned, we'll talk about fluorescent lights. Well, fluorescent light is just an arc, but it has lower heat than an incandescent light. Well, anybody know what generates light? How we generate light? All the ways, whether you're talking an LED, a fluorescent light, or an incandescent light, all of them generate light the same way. It's by electrons turning corners. Okay? If an electron goes straight, no light. But if an electron turns a corner, that change in momentum and energy as it turns the corner, it gives off radiation. And if it's hot enough electron, the radiation will be in the visible range. If it turns the corner very slowly, it'll be in the infrared range. If it turns it real fast, you'll get the ultraviolet. And if these things do other things, actually you get the X-ray. But in the visible range, it's really basically just electrons turning corners rather than going straight. So, anybody know how you generate light with an incandescent light? You heat things up real hot, right? That little tungsten filament, that's what Thomas Edison invented, right? He used a graphite filament, but eventually they found tungsten was better. They just heat up real hot. All you're doing is you're running a current through it to heat it up, and those electrons interact with the lattice, and they have to turn the corner when they bump into the lattice. And that slows them down. If they just went straight through, no light. But they don't go straight through. Okay? And so basically you heat the whole thing up and you get vibration of these electrons, movement of electrons, and you get light off with temperature. Okay, in a LED, you basically have electrons changing states and whatnot. And you can argue whether they're turning corners or not, but basically you've got electrons changing energy levels and you get light. If you're going to try to get white light at all wavelengths, it's eventually going to have to be electrons turning corners so you can get all wavelengths. But in a fluorescent light, you essentially do the same thing, but now instead of like an incandescent light, the electrons actually do go a fair distance in a straight line because that fluorescent light's in a partial vacuum, right? You ever broken one? You know, it's in a vacuum, right? It implodes. And you have to be careful about breaking them, okay? Actually, an incandescent light is also at about a half an atmosphere, but that's only because the argon gas inside has to expand as it gets hot. And so you don't want it being more than an atmosphere when it gets hot, or you'll burst your fragile light bulb. So there's a slight vacuum in an incandescent light, but there's more in a fluorescent light because you actually want a long mean-free path and to get those electrons going fast so that when they hit a molecule or another gas atom, that they can slow down and give off their energy. Okay? Well, the difference here is in an incandescent light, you have to heat up all the molecules, and everything has the same temperature, and it's very hot in order to get to the wavelength that you see light. In an incandescent light, it's much cooler. You can hold your hand on that thing, and it's not hot, whereas you don't want to do that in a fluorescent light, but on an incandescent light, you burn your hand, right? And so it's less energy, and the reason is you have a long mean-free path in the gas, in the fluorescent state, and the things will travel 100 times their atomic separation or 1,000 times and get accelerated, and therefore it turns out the electrons have high temperatures but the ions have low temperatures. Well, the ions have all the mass, so a fluorescent light is lower in temperature because you're not heating up the gas atoms, you're only heating up the electrons. In an incandescent light you have to do both, so you're wasting all this energy. So fluorescent lights are more efficient because I've found a way to only heat up electrons in the gas phase, whereas an incandescent light I have to heat up everything, solid atoms and electrons both, in order to get those electrons moving and stop them. And an LED, it's even cooler still, right? That's how you get these low power flashlights with batteries that last for 100 hours, right? Very bright, because you're not moving those, you know, you're really selectively picking out individual electrons and heading them in one direction, not just in random directions, okay? So it's even more energy efficient. So in every case, if you get back down to the fundamental physics, how do you generate light? You stop electrons. You stop them or bend them so that they give off their energy, and they give it off as light if they have the right amount of energy. Well, Thomas Edison came up with a very inefficient process because in order to get those electrons to do that, he had to heat up all this solid. A fluorescent light is a little bit better because I accelerate the electrons without really heating up the gas molecules very much. And then in a semiconductor, I'm actually even more efficient because I'm not just setting things off in all directions, I'm actually focusing it with a laser. Okay, light emitting diode is a little laser, right? And I'm really focusing and controlling how I put the energy into the electrons, and I keep everything else nice and cool. No waste heat. Right? So, if you actually understand the basic physics of something, you can actually start figuring those things out. I never read any of that in any book.
Speaking of LEDs, what's the thing up in the corner next to the wireless antenna?
That? This thing? Oh, this one, the white one or the black one?
The black one.
I don't know what the black one is. I assume it's something to do with the audio-visual in here. In fact, it's probably a wireless hookup, maybe a router.
Oh, the white one is.
Well, no, the white one is a fire alarm thing, isn't it?
No, that's the wireless.
Is that the wireless? I got them in the hallways around here too. Okay, maybe. Okay, that's the wireless. Okay, fine. I don't know what that is, unless it, well, I don't know. Don't know. I don't even, can't even see it. So,
What are those things you put all over the standards?
actually, when I was teach the undergraduates, I sometimes teach a lesson on how to estimate things. I've told you this story. And I have various things on how to estimate things. Like for example, this is actually not a bad one for how to think. If I asked you the question, we know the tallest mountain in the world is Mount Everest, right? Except that's not really true. Anybody know what the tallest mountain in the world from its basal plane is? Mauna Kea. You're right. I mean, Mauna Kea is a little bit taller than Mauna Loa. But it's from this basal plane, they both start out at the bottom of the ocean, and they rise up to a little bit less than Mount Everest above the water and above, the sea level. But they're actually slightly taller. Well, that's one little fact that you might or may not know. But the question is, okay, would you expect mountains on Jupiter to be taller or shorter than the maximum height of mountains on Earth?
Short.
Shorter, why?
Because
Right.
I would think that there's more, you've got more gravity, so things
Exactly.
tend to be squished.
If I had infinite gravity, everything would be a perfect sphere, like a ball bearing, right? Just like surface tension will turn things into a sphere, okay? If I have infinite gravity in the limit, there would be no mountains. They'd all get crushed. And in fact, it turns out we don't know about mountains on Jupiter because it just sort of gets thicker and thicker, okay, as we can't see down in there. But we do know about mountains on Venus. Venus. Venus, the tallest mountain on Venus, is 45,000 feet. And Venus has about 0.6 the gravity of Earth. And if you take 30,000 feet and divide by 0.6, you get something very close to 45,000 feet. And that's because rock, or minerals, or whatever these things are made out of, they have about the same type of strength anywhere you go. Okay? Now, on Jupiter, it may not be the same type of rock. It might be liquid nitrogen. It might be solid nitrogen, for all I know, whatever it is, or solid carbon dioxide or something. But basically, between Earth and Venus, they're made out of rock. Okay? And rock has the same mechanical properties. So whichever one has greater gravity, it's gravity that limits the height of mountains. Okay? So that's one way to estimate things. Another way to think about things, you ever wonder about what controls the height of a tree or a bush?
But it's surrounded trees.
The desire to use the sunlight.
You got to get water to the top. Okay? You're not going to have green leaves at the top, and it's not going to grow at the top unless it gets water up there. How do you get water to the top of something? Capillary action, right? So therefore, do I expect some sort of pear tree, which grows to a maximum height of 25 or 30 feet, to have smaller capillary cells than a redwood, or larger capillary cells than a redwood? Larger, because the larger the capillary diameter, the shorter that is the capillary force that pulls the water up. Redwood should have very fine grain. Anybody who's ever seen redwood knows it's got a fairly fine grain. Okay? And you go in there and look at those capillaries, you'll find there's a correlation in all this. It all gets back to knowing about surface tension of water and what pulls water up to the tree. So a lot of times in some of those types of things, you have to think your way through it, but you have to say, well, what's the fundamental controlling thing? And then if you know what the fundamental controlling thing is, you actually, even from your high school chemistry and physics, but hopefully definitely from your MIT chemistry and physics, should be able to figure out what the controlling things are. So anyway, so I used to do this thing with the students, and I'd give them a homework problem, say, okay, come back, this is a little seminar type thing with a few small number of students, and I say, come back, and everyone will come back to the next class, and your homework is to come back with a problem that all the rest of us have to estimate. Okay? So, what's your question?
I was just going to say on the tree thing, I know that we learned in high school that capillary action doesn't count for the water going up the tree to a particular height. I can't remember what the height was, but it wasn't to the top of the tree. It only can handle, capillary action is only good for the first thing on the size of the tree, and the capillaries we're talking about a certain height. But then above and beyond that, there's a process called the stomatic process, where in the leaves they have these little, it's called stomates, but it's basically a pore in the leaf where water vapor or whatever gases can leave, and
It sucks things up.
yeah, as a molecule leaves, it creates a vacuum in the tube and it pulls the rest of the water up. It's kind of like a
It's like negative pressure as well. So you got capillary action takes it up a certain distance, but then that action, but still, that action still is going to be dependent on pore size and everything else. So you're right. I'm sure it's a combination of the two. So anyway, I had the students come back with things, and one of them came back with, and they go on the web, and they said, one of them said, well, how many pounds of cornflakes do we sell in the United States each year? And I actually got within a factor of 3, because you estimate how many people there are, how many people eat breakfast, don't eat breakfast, you know, and how many people are going to eat cornflakes versus don't, and you end up, yeah, I got within a factor of 3, which actually, for just, you know, a question, the one question I had no idea of any way, because there's no physical basis for it, okay, that I could think of. The student asked, how many shares of Microsoft trade in a day? Maybe some financial guy has some basis for it, but I had no idea, no clue of how many shares of Microsoft trade in a day. So you can't estimate everything, but you'd be surprised at how many things you can estimate, okay? If you just kind of put your mind to it and how close you can get, okay? Okay, other questions? Good progression, guys. Okay, now let's go back to adhesive bonding. The problem is I've already given these lectures before. So, well, we talked about the Stefan equation and how the joint thickness is important, but also the viscosity is even more important. And we talked about the 3 ways to change the viscosity of an adhesive. So you can put it on easily, low viscosity, and it holds its strength later at high viscosity. Our solidification, those are the hot melts, or phase changes, someone said it. Chemical reaction, those are the epoxies, the anaerobics, and cyanoacrylates. And then solvent removal, which is probably one of the most common, and that's basically glues, that, you know, Elmer's glue, wood glue, and things like that. We also talked about the tremendous disparity in the price of adhesives from, you know, something as low as 10 cents a pound to $400 a pound, depending on the quality of the adhesive, the durability, chemical resistance, and everything else. So I actually do have some other adhesive examples. This is a piece of the liquid hydrogen tank for the X-33 space plane. The X-33 space plane was supposed to be a replacement or a demonstration replacement for the space shuttle. NASA had a $1.3 billion program with Lockheed Martin, and they were going to build this half-size space shuttle that was going to fly from Edwards Air Force Base to Dugway Proving Grounds in Utah. They were going to have like 11 flights, suborbital flights with this thing. And I don't know if some of you remember or have heard about in the early 90s after the first Gulf War, the Defense Department got into rapid prototyping. Wanted to prove that you could do things in a short period of time. Well, NASA picked up on this and gave a contract, $1.3 billion contract. And part of the contract was to do this, design this from, you know, paper and pencil and computer design to first flight in 33 months. Okay? So it's tight schedule, and of course if you compress the schedule, you reduce the cost and everything else in theory. So they first spent their first 4 months of their 6-month design budget trying to figure out how to do this in a ring stiffened cylinder type of design. I didn't bring a picture of it, but the X-33 space plane was going to save weight. We already talked about it. It's like a $100,000 or $10,000 a pound to get weight in space. The space plane looked something. The X-33 looked something like this. Had the engines off the pack, but basically it had 3 tanks. I think I may have mentioned it to you before. It was a hydrogen tank, and an oxygen tank, because that's one of the lightest fuels you can come up with, and it's H2O is your fuel. But these 3 tanks are actually the structure. The outer stuff was just skin. And so this gets into the whole design philosophy of multiple functions for each material. Okay, right now you build an aircraft and the outer skin actually is the structural part, and then you put the other things on the inside. Well, the fuel tanks were actually the structure that held everything together, and the skin was just this sort of shroud that gave you aerodynamics. Okay, and so these 3 tanks were critical. This one was actually made out of aluminum because of the problem of pure oxygen. If you tried to make it out of a polymer tank, polymers tend to burn, and pure oxygen tends to be a good oxidant. Okay, and so these 2 were going to be made out of composites, so they'd be nice and lightweight. Because that was one of the things, one of the big problems on a single stage to orbit vehicle, which is what this is supposed to be. and single stage to orbit. You don't throw off your extra tanks, you know, like they do on the space shuttle and drop them into the ocean. You're going to be able to recover this whole thing. You're going to get to orbit and you're going to be able to reuse it. It's reusable single stage to orbit. That's going to cut your costs down from $10,000 a pound to $1,000 a pound into space. Okay? Tremendous savings if you can do it. So they had this rapid prototyping program to build this $1.3 billion prototype, and they tried to do for these space shuttle main tanks, and each one of those hydrogen tanks is about the size of a small 2-story house. Okay, just to give you an idea. Okay, and you know, length to width similar to this. And so they first thing they kind of looked at 3-dimensional woven graphite composites. And then they got a price for this, because to make these kind of, you know, this is a ring stiffened cylinder. I mean, this is, you guys, you know, the submarine fleet, you know about this. A ring stiffened cylinder with, you know, stiffeners on it. That was going to be the basic design of this thing. And these were going to be graphite woven composites. And the way you make these 3-dimensional woven composites is you have a bunch of people sitting there with a needle and thread. And the thread is a graphite thread. And they just kind of make a 3-dimensional weave. Well, can you imagine how labor intensive that is? So they got a bid on that, and they found, oops, we just exceeded our budget by about a factor of 10. And so they had to think of something real quick, and they had about 2 months to keep their budget going. And they came up with Hexcel foam, which is Nomex, which is the stuff, you know, the firefighters wear Nomex suits. It's basically Kevlar, that's DuPont's trade name. Nomex is Monsanto or somebody else. So you can buy this Hexcel foam, which is Nomex or Kevlar in a honeycomb. You can just go buy it off the shelf. And then you can also buy off the shelf a graphite epoxy composite tape that you can wind up on a big form. And so this is what they decided. They were going to have 2 layers of graphite epoxy as a skins on either side, and they're going to have Hexcel foam, and they were going to make the whole thing a cellular composite structure as opposed to the spring stiffened cylinder composites. And they decided, oh, we can do that. All we need is an adhesive to join the graphite epoxy to the Hexcel. Well, they don't have time to develop something. That's one of the things they're trying to demonstrate, that you can do things off the shelf. Remember this kind of thing in the 90s? You could do anything off the shelf, right? And quit trying to develop things specially. So they went to the website of 3M, and they found they had a nice aluminum sheet adhesive that they sold for aerospace applications, and it said on the little PowerPoint type presentation, had a 10-day shelf life for this adhesive sheet. Okay, this is an epoxy, and this is an epoxy sheet on a release film that you store in a refrigerator at minus 10 degrees centigrade or something, because if you stored it at room temperature, it would actually slowly cure. The chemical reaction would change the epoxy and the adhesive would harden up. Well, that's not good. But it said that after you take it out, it said, bullet point, 10-day shelf life. They said, okay, we figure we can put these together in somewhere like 4 to 7 days, wind them up, get them into the autoclave, world's largest autoclave in Sunnyvale, California. Just happened to be the perfect size for building one of these 2-story houses. Okay, so they build them, and they have to build. They needed actually 8 of them, because there were 4 lobes for each of this, so that's 8 lobes that make these things. And they were going to build 2 spares just in case. And one of the problems with laying up composites is this stuff. You have to build special formwork out of steel or aluminum or whatever, and it's got to be metal. You can't make it out of wood, which is cheaper, because it's got to go in the autoclave and be heated up to cure the epoxy. When you cure the epoxy, you harden the adhesive so it has strength. So it turns out they did all this, and 2 of these 10 things came out with blisters on the skin. The surface delaminated from the Hexcel foam, and if they looked at it carefully, they would see if this is the Hexcel foam and this is the carbon composite, or the graphite epoxy composite, They didn't have, what they wanted was a nice adhesive bond where they got flow of the adhesive and they got a nice wetting contact angle. You want to get wetting of your adhesive. What they actually got, if I pass this around, you'll see they actually had the adhesive with no real contact there, lousy contact. It didn't really wet. And so they went around, and so if you look on the end of this thing, you'll see a little layer, different color layer of adhesive right there between the graphite and the brown XL foam. And you'll see that you don't have a nice fillet, okay, that formed in here. You got a lousy fillet, and it turns out they went back to find out, and lo and behold, they went back to 3M and said, you said it had a 10-day shelf life, and they put all these together in 3 to 7 days, which is well within the 10-day shelf life. And 3M says, oh, well, yeah, we say a 10-day shelf life. Here's the graph. Okay, this is strength of the adhesive versus time, and you lose strength as the stuff hardens up and doesn't flow, doesn't give you good wettability and stuff. And that's where 10 days is, folks, at the 10% strength level. Okay, so this is 10 days, and 3 to 7 was in here. These guys are figuring they're going to get this strength. Some of these things came in where the epoxy had already hardened up. Okay, so there's several lessons there. One is the danger of taking bullet points for data. Okay, the PowerPoint, syndrome. Okay, that you can summarize real data as a bullet point, and you can't. And the other thing is, you got to really understand what's going on. So they canceled the $1.3 billion program after they put this in a liquid hydrogen test in Huntsville, Alabama, because not everybody has 10,000 gallons of liquid hydrogen around. Huntsville does. They put it in, and after 30 minutes, the thing delaminated, and they killed the program. Each one of those 2 tanks, the hydrogen tanks, cost about $50 million. They weighed 4,000 pounds apiece. I don't know if I told you this before. That's $12,000 a pound fabricated for that. Yeah.
Sales reps aren't tech reps.
That's another. Okay. Sales reps, they're.
You gotta ask them too. Are you willing to put that on paper?
Right.
Sign your name to it.
Well, it turns out another thing that was part of the problem. And if you want to buy in, if someone wants to put another $1 billion in, the people at the Lockheed Martin Skunk Works will sell you what's left of the X-33 space plane. Okay. And in fact, if you want an extra liquid hydrogen tank, not been used, it's sitting out there at Baltic, okay, and they'll give it to you cheap, I'm sure. The other one got torn apart, and that's just a piece of the other one. But there's lots of lessons to be learned from a situation like that, I guess. But anyway, it shows the problem. One of the problems with adhesive bonding. I guess some other people asked me about. Another thing about adhesive bonding is cleanliness. Okay, and let me first put up. Before I get to that, we talked about Young's equation, and you want to get stuff to flow. You'll get things to flow if you actually can take a high surface energy material. This is Young's equation. Will basically tell you this. If you have a high surface energy and you can get a liquid that wants to cover that surface, the liquid is going to cover that surface if the liquid vapor surface energy is lower than the solid vapor surface energy. Okay, it's going to want to contaminate the surface if you can reduce the energy of the surface. If you reduce the energy of the system, and the thing will occur spontaneously, thermodynamically. So the thing will flow if I have a high energy surface. What are the highest energy surfaces? Well, they're metals. Okay, metals have these very, very high surface energies because even though they may not have the highest bonding strength compared to covalent and ionic, there are a lot more electrons that are involved because metals share electrons over a much greater distance into the metal. So it's the first 2 or 3 atom layers of metals rather than just the top layer of atoms in covalent and ionic that contribute to surface energy. So it turns out metals typically have like 3 times the surface energy if you get them nice and clean. But metals, by the same token, want to get contaminated. Virtually anything else in the world will contaminate a metal. And if I go back to the beginning of this book, which is the one I threw in the trash, in the beginning here, this was done. This book was written by people, or this chapter. So the book was edited, and the first chapter was written by a guy at Xerox Research Center. And they're looking at bonding of polystyrene to graphite, polystyrene to silver, polystyrene to ceramics and stuff. And this is the bond energy in electron volts. Okay, they're actually those shifts van der Waals constants, but anyway, polystyrene interacting with other materials. Why would Xerox spend all this time looking at polystyrene bonding to other materials?
That's part of the toner.
The basic toner is a piece of polystyrene, a little polystyrene particle, and you fill it up with carbon black, and then you put some other things on it to give it an electrostatic charge. Okay, so it's got some other things in it. But basically, when you melt the toner, you fuse the toner, you know, laser printer, the sheets come out warm, because you just melted these little polystyrene particles into the surface. Okay, so it's polystyrene. So that's why Xerox knows more about polystyrene adhesion to other things than anybody else in the world, because that's their business. They make millions and billions of pounds of polystyrene powders every year. Well, if I'm talking about polystyrene to metals, I have very high bond energies. If I start getting down here to ceramics, I get lower bond energies, and if I get down here to water and stuff, I get some of the lower bond energies. The surface tension of these metals is like 1.5 joules per meter squared. The surface tension of water is 0.072. Okay, it's much, much less. The lowest surface energy materials, this comes out of Zisman, if I remember, maybe not, maybe it comes out of one of these things. But if I look at my covalently bonded things, this is polyvinylidene chloride, which is 2 chlorines and a hydrogen. If this was polyethylene, it'd just be all hydrogens on a carbon backbone. And this has a critical surface tension half of water. If water's 72, this is 40. Okay, and then come down here. Well, here's polyethylene. Okay, it's 31, 20, and so 30. Well, 36 is half of the 72. So, and the lowest surface energy of anything is carbon backbones with fluorines. All fluorines. This is 3 fluorines and a hydrogen is 22. Teflon is 18. Okay, 1/4 of the surface tension of water. There actually are some others that are around 16 or 17, but they tend to be gases rather than solids. But Teflon has the lowest surface tension of anything. So if I want to contaminate a surface or make it such that things don't adhere to it, I want a Teflon surface, which is why I think I mentioned, you know, in the beginning class, my glasses, when I got new glasses this spring, they told me I could get a Teflon coating, which would keep them cleaner. And I paid the extra money for the Teflon coating because I know that's true. It will. The dust will not stick to the Teflon as readily. That doesn't mean they don't get dust, and I don't have to clean them. But I don't have to clean them as often. Okay? But the general form of adhesive bonding for most things is not just simple surface tension wetting, although it's important, but it's mechanical interlocking. And that's what we call type 2. This gives you an idea of what happens in tire cord. Okay? If you drive on steel belted radial tires, right? You got to bond rubber to the steel cord. If you don't, the thing's going to delaminate. You lose your tire tread, and the steel cord doesn't do you much good. So when they first started doing this, they were just trying to bond rubber to steel. And it can be done, but it doesn't work very well. And they found if they plated it with copper, they got a much better bond. But they found later, if they plated it with brass, copper zinc alloy, what they got was, this is copper zinc brass. They form a zinc oxide surface, a zinc sulfide surface, because where's the sulfur come from? I'm dealing with rubber. Vulcanization of the rubber. The rubber has sulfur in it. That's what Charles Goodyear did. He took sulfur and put it in with the gutta percha and polymerized it with the sulfur. So the sulfur is up here in the rubber, the copper and the zinc are down here, and you form these zinc sulfide layers, copper sulfide layers, and then copper sulfide, zinc sulfide, and you form these little dendrites, these little pillars, mesas, growing into growing off the surface that allows mechanical interlocking of that rubber. Okay? So it turns out it's mechanical interlocking. If you come up here to the top, this is basically adhesion of various materials to natural rubber. Iron and steel, there's not very good adhesion. copper, just straight copper with a little bit of excess copper sulfide, not much adhesion. Copper plated steel turns out to be pretty good. The best, with values up to 1,200, whatever the units are, it's newtons over 64 per millimeter squared. Obviously, they're looking at a 64 square millimeter sample, okay, measuring it in newtons. So 1,200 newtons per 64 millimeter squared. I don't know why they can't take 1,200 and divide by 64, but anyway. In any case, it turns out you brass plate the wire. And so if you ever see a complete delamination of rubber from steel tire cord, you need to go in there and look and see if they did a good job of plating of the wire. It should be brass plated wire. Okay. So that's mechanical interlocking. Now, I have another story on adhesives. I only have 3 little adhesive stories, but or things. This is Millennium Cookware by Faberware. Okay. And actually, there's a cold welding story here on the bottom. This is a very expensive pot. This is over $100 if you buy this from Faberware. It's got a aluminum base, and to get this aluminum base to bond it to the stainless steel, they sand both of them. They roughen up the surface, and then they heat the aluminum, put it in a little, warm it up, about 300 degrees Fahrenheit, in a furnace, and then they take the steel pot, which are already drawn, and the guy puts it on top of a stand, a steel stand. Then he takes one of these aluminum discs out of the furnace, puts it on top, and he keeps his hands out of the way, hits the button, and this big 10,000 ton press comes down and goes wham! Okay? Now, you got lots of mountain peaks because you roughened it up with sandpaper to begin with, but all you did was straight downward pressure. Okay? So where's the shear to get the good cold welding? Turns out there's not any. They're getting lousy cold welding. But it turns out in this application, they want lousy cold welding. If they had 100% bond, what would happen when this thing heats up because of thermal expansion? Well, it would bow. Okay? The aluminum would expand more than the steel, even though it's thicker, but it still would expand more, and this thing would bow, and the last thing you want is a pot that has a dish this way and rocks on the stove. So someone's going to knock it over, right? So it turns out they didn't know it. I had to explain to them it was a lousy way to get a cold weld, but they probably only wanted 10 to 30% bond. They probably wanted some voids in there to allow for the differential coefficient of expansion on a microscopic scale. So that's cold welding there. But on the inside, what happened is they came to me and they said, they bought this pot, and it had cracks in the side. And they said, we made these pots, we've got Teflon on the inside, and we shipped them to Japan, and then once we shipped to Japan, when they got off the boat, they had these cracks in them. And I didn't bring my magnet with me. I should have brought my magnet. This thing used to have a magnet with it. And what I did, so we sit in my office, I went and got a magnet out of my desk drawer, and I said, and you could feel there's no magnetism down here, and there's magnetism up here. And that's because this is a 304 stainless steel, and 304 stainless steel changes crystal structure as you deform it. And in order to deform it to the shape, to form a pot, there's more deformation up here than there is down here. Down here, all you do is fold it over the corner. Here, you're actually stretching it and changing its shape significantly. And what these lines are, we later had a student take a calibrated magnet, same type of magnet that is used to measure the amount of ferrite in stainless steel weld metal, and showed you could plot the relative magnetism increasing across here because this stuff was turning to body-centered cubic iron. Well, okay, so we got body-centered cubic iron. Why are we getting these cracks? Well, first of all, they told me they're delayed cracks. They didn't show up until I got to Japan. Well, what does that tell me? Delayed cracking, to me as a metallurgist, means hydrogen embrittlement. Hydrogen embrittlement doesn't occur in 304 face-centered cubic stainless steel. It does in body-centered cubic. These cracks were all starting up here and running down here and stopping because they ran out of body-centered cubic iron. Okay? So it all fit together. And I said, well, where's your source of hydrogen? And they said, oh, in order to bond the Teflon to the steel. How do you bond Teflon to steel? It's got lousy surface energy in order to try to really bond to things. It's one of the most difficult things to bond at all. In fact, that's why you put it in here if you want a non-stick surface, right? Well, they plasma spray the inside with a stainless steel powder. And what's the spraying gas? It's argon hydrogen. Where's your hydrogen come from? It comes from your spraying gas. I said, okay, well, you're going to have to. And so what they ended up putting on here is they plasma spray a porous powder of stainless steel inside this thing, and then they impregnate it with Teflon. So you get excellent bonding of the Teflon. You pay a premium price for this pot, and it'll crack on you because they got hydrogen in it. Yes?
If I understood you earlier, I thought that Teflon and essentially low surface energy would bond very easily to high surface energy materials like metal.
Except the steel has already got oxide on it. It's already got oxide on it.
And lower surface energy.
And so nothing wants to bond to the Teflon because the Teflon has got a low surface energy to begin with. Nothing else is going to replace this low surface energy of the Teflon. The Teflon already exists with the surface, a low energy surface, so it doesn't want to bond to anything else. If I had perfectly clean steel with no oxide on it in a vacuum system that didn't, you know, when we got the Langmuir again, 10 to the minus 8 atmosphere seconds, and I had absolutely clean metal, and I put Teflon on that, I would get the strongest bond I'd ever get. But this surface is already contaminated with oxides on it. It may have a high surface energy, but the Teflon surface has already got a low surface energy. It's the two surfaces that come together have to reduce the surface energy. Okay? So the Teflon, nothing sticks to Teflon because it's got a low surface energy. I can bond the Teflon to the surface by essentially making it mechanical interlocking. But the mechanical interlocking means I need a very rough surface. These are expensive pots because they've gone to a very expensive way. They're not just sanding it. You go get a cheap non-stick cookware, all they did is sand it to get a rough surface. These guys ended up with a porous, thick layer so that Teflon can be impregnated down into the pores. That stuff's really stuck on there, okay, by very good mechanical interlocking. So like a sponge soaking up the Teflon. Now, part of the problem, in fact, that was one of the things I wanted to talk about. I've never done this, but one thing, sometimes people model a pour like this, and they'll say, okay, I've got a liquid, and the liquid has to wet the surface, because if the liquid doesn't wet the surface, it can't get down in the pore. Surface tension is going to keep it out of this little V-shaped solid pore, right? This is my solid, and here's my liquid up here, and I've got to in order to push that into the surface, I have to overcome that surface tension. And Teflon on the surface, or not Teflon, but a drop of water on Teflon is going to have a very high surface energy, lousy Young's equation in terms of the high contact angle of water on Teflon is going to mean that the water couldn't get down inside this pore. And what I've read, I haven't done it, is there is a trick that you can bond water to Teflon, okay, or ice to Teflon. And what you do is instead of starting out with a piece of solid Teflon with a very low surface energy, you start off with this piece of solid Teflon, but instead of putting water on it, where the surface contact angle of the water is 72 and the surface contact energy of the Teflon is 18, why would the water want to contaminate the surface of the Teflon? It's going to raise the overall surface energy of the system to take a 72 and an 18. It's going to have a high contact angle. You actually have the surface tension force resisting the intrusion of this liquid into this pore. So you're not going to get mechanical interlocking. But I've been told if you take steam and condense it on cooler Teflon, then what's going to happen? The steam is going to go in here as individual molecules, and it will go in like this. And the contact angle now is holding the Teflon in the surface of the material. It's not keeping it out of the pore, it's holding it in. So if I have something like this, and I surface saturate this whole thing with steam, And now I put water on there and I freeze it, I've got my mechanical interlocking. Because I now got my liquid down inside my pores. Okay? Because I vapor deposited the liquid as opposed to trying to flow it in as a liquid. I can't flow it in as a liquid when I have a very low surface energy surface. So the point of all this is that in order to get good adhesive bonds, I have to have a clean surface that has high energy that allows the liquid to flow into those pores to make the mechanical interlocking. Or if it's type 1 bonding, I just have to have good clean surface so that it wants to flow across the surface and form nice thin surfaces. Okay? I've never done that with the Teflon, although there have been a couple of times in consulting I suggested to people that they think about that as a way to solve a problem on a surface. So if you actually start, again, thinking about the basic physics of what's going on, here the problem is the liquid doesn't want to go in there if the solid pore has a lower surface energy than the liquid that you're trying to put in there. It's not going to wet it according to Young's equation, and you're not going to be able to push it down in there. But if you put it in there in the vapor phase, you actually can transport it in there, and it actually wants to stay there.
In a same type of situation, but say you're trying to paint a surface that you rough up first.
Yep.
The paint goes in the pore because its surface tension is less, or
The paint is formulated so some of those solvents they put in there help give it a surface energy that's going to be compatible with that rough surface and is going to wet that rough surface.
yeah.
But and so you want to get the paint down in those pores.
That's why you want to rough it up.
That's why you sand the paint before you put a second coat on, for example. Some people do. You want to rough it up so that you get mechanical interlocking. If you have the paint film should form, just like Jupiter with its gravity, a nice smooth surface. If you now try to put something on top of there, the only thing you're going to get is type 1 adhesive bonding, right? But if I roughen up the surface, I'll get some mechanical interlocking. As long as the paint wants to wet the liquid paint wants to wet the dry paint, okay? Which they should have formulated it with solvents or other things that allow it to wet the surface. They've got to have a low contact angle, theta. If it beads up, it's not going to be good bonding, okay? So the paint, if you actually put a drop on a already painted, a drop of wet paint on an already painted surface, if it doesn't want to kind of flow out and form a fine contact angle, you're not going to be getting good bonding.
That's usually not a problem with the initial coat because it's.
Well, the initial coat, it depends on what you're coating. If it's metal, you got to roughen up the surface with phosphating or anodizing or whatever to roughen up the metal surface to get the mechanical interlocking. Or you end up with a something like a primer, and the primer actually might be slightly acidic, let's say. It may actually eat away the metal surface, corrode it slightly to roughen it up chemically, okay? And then the primer is got solids in it such that it doesn't form a nice smooth surface. What primers are ever glossy? None of them. They're all kind of a matte finish. Why? Because they're designed to give you a rough surface. When the solvent goes away and you leave the solids behind, some of the solids will be sticking up like little mountain peaks, with a rough surface, right? If you want a glossy finish, the worst thing to paint over for adhesion is a glossy surface, and you got to roughen that up with sandpaper. Okay? Okay, that's enough for today. See you tomorrow.